All right, good morning. Yes, we can get started now. Hopefully you can all see my see the screen that I'm sharing with you, the notepad I always use. If you don't see it, please let me know. So a couple, well, really just one thing. The exam has been graded and published on Gradescope. So if you haven't got a chance to take a look at it, please do. If there's any issues with the grading, with points, please let us know, we can fix it. And I'm not sure, I think there might be a quiz the next week, but I have to double check. Please also check your calendar and see if we have a quiz next week. So for today, I'm just gonna go through a few examples with power series representations for functions. And if you have any questions, please let me know. Feel free to unmute yourself or even just type it in the chat box, whichever is most convenient for you. I want to begin with by writing the I guess where the power series come from. What's the easiest example to begin with? So the easiest example that we're familiar with is a geometric series in the form of 1 plus x squared. And that geometric series, we can use sigma notation, which is n from 0 to infinity. So this is the n equals 0 term, this is the n equals 1, and that continues. And the expression for each term that is just x to the n. This is the geometric series. And this series is convergent if the ratio, in this case, the ratio, so if you recall that the ratio is, the geometric series is always a times r to the n. R is the ratio, in this case, the ratio is x. If absolute value of x is less than 1. Right. Now, since it's a geometric series, then we can write down the sum formula for the case that's convergent. So the sum formula, which is just the first term of the series 1n equals 0, which is just 1 in the numerator, divided by 1 minus the ratio is x, 1 minus x. So for a convergent geometric series, there's 3 representations. One is the expanded form, one is the sigma notation, and also the sum formula. Now, how is this going to help us? Well, it helps us because if you think about this is some function of x, let's just see, we know that some function of x, then the sigma notation sort of, it's basically the power series representation of this function. Right, so that's the connection between these two. And then you can set them equal. But what I'm going to do is I'm going to set them equal, but instead of using lowercase x, I'm going to use a capital X for a more general case. So for f of x is equal to 1 over 1 minus capital X. So suppose we have this function in this form, then we can write down the power series representation, which is just sigma n from 0 to infinity, capital X to the n. Now this series converges for capital X in the absolute value is less than 1. Just basically copying what I did with the geometric series example above. But here I use the more general notation capital X to distinguish from the lowercase x, because a lot of times a function given is in lowercase x, and if we don't distinguish them, then it could be confusing because they could have different meaning in different steps. So that's the the sort of, I guess, the first technique, which is using the geometric series, but generalized using capital X here. So whenever we have a function, if we can put into this form, then we know what the power series look like. We literally just take the capital X and put it into the sigma notation. So that's a starting point. Here's the first example. So suppose we have this example f of x, lowercase x now. So capital X is only for the general form, but lowercase x is, that's what we normally use to define a function. F of x equal, let's just see 10 over 1 plus x to the 7th power. This is a function, and we want to find the power series representation. We want to write it in terms of sigma Cn coefficient, and then x to the n, or some form equivalent to that. What do we do? Well, we only know one trick, right? Which is the one that I wrote in purple above. So if we can somehow take this 10 over 1 plus x to the 7, and then we can convert it into 1 over 1 minus something, that would be helpful. So what we can do, we can rewrite it. The numerator, I want it to be 1, but I have a 10. So I'm going to put 10 aside from the numerator. So that will give us a 1 over 1 plus x to the 7. So that's one step close to the form that I wanted. So the numerator is 1 now, it's good. The denominator also begins with 1, that's good. But I want a subtraction instead of an addition in the denominator. So I'm going to rewrite the denominator using subtraction. 1 over 1 minus a negative, right? When we minus the negative, it becomes positive, x to the 7th power. So now if you look at this, except for the 10, so this part is basically the 1 over 1 minus capital X form, with this parentheses part being the capital X equivalent. Right, so let me write capital X in my general formula is equivalent to negative x to the 7th power. So now I have the correct form, which means I can find the power series for this boxed part. So that will be 10 times sigma n from 0 to infinity, capital X to the n, but capital X is negative x to the 7, so that's a negative x to the 7 raised to the power of n. Any questions on that? So we're close. We still have a 10 in front. We still have this negative x to the 7 raised to the n inside the sigma notation, but I want to write it as coefficients times x to a power, right? So what I'm going to do is I'm going to bring the 10 inside, and I'm going to separate the negative from the x to the 7th power. So that's sigma n from 0 to infinity. 10, if I bring inside, it's just 10. And then negative, I can pull out the negative 1, becomes negative 1 to the n. And then x to the 7, but then there's another exponent n, so x to the 7n. So this is the final answer, the power series that we're looking for, because this is the Cn. This is sort of the x to the n. It's x to the 7n, but it's equivalent to x to the n part. Any questions on this? For now, if you can take the given function and then convert it into the 1 over 1 minus x form, then it's a lot easier to find the power series. If you have any factors or constants that you pull out in the beginning, just bring it back inside later. Now, the next thing I want to kind of go over is the radius of convergence. which says for a series sigma n from 0 to infinity x minus a, well, that's a cn x minus a to the n. If the series converges for x minus a absolute value less than r. So if there's some r value when x minus a is in the absolute value is less than that number, the series converges, then this r is what we call the radius of convergence. In the form that I wrote above with the capital X, so we know that the series converges when capital X absolute value is less than 1. Now, if we put in the similar form, you can write as capital X minus 0 absolute value is less than 1. The 1 will be the, so this 1 is the radius of convergence. So R equals 1 is radius of convergence for this general case. Now, for this example, sort of jumping back to the example we just finished, how do we find the radius of convergence? Well, you could take the final power series and try to figure out the equivalent R when you have x minus a is less than R. You can try to figure out what the R is. Right? But there's another way to do it, which is using the fact that earlier we had capital X equals negative x to the 7. We use the general formula to find the power series. So it's this part, that's what we can use. So that part, the 1 over 1 minus capital X, we know that's convergent if capital X is less than 1, right? That series converges. Now, what is capital X? Capital X is negative x to the 7. So we're just going to plug in negative x to the 7 directly to replace capital X. That's less than 1. That has to be true. Which follows that we can solve for x, lowercase x from here, which is x to the 7th absolute value less than 1. Take 7th root, absolute value of x less than 1. And then this we can just write as absolute value x minus 0 less than 1. And this is in the form of x minus a less than r. So that means the r is equal to 1, which is the radius of convergence. So instead of like taking the final power series, try to figure out what the a is, what the r is from there, we take the substitution we did earlier with capital X in an absolute value being less than 1 to figure out the equivalent inequality for lowercase x and to find the radius of convergence there. Any questions about finding radius of convergence? I'm going to go through another example, hopefully helps a little bit more. So the next example I have is f of x equals x cubed over x plus 2. And in this one, the first thing I'm going to find the power series representation. And then we can find the radius of convergence. So let's find the power series representation. So the trick we know is that if we have 1 over 1 minus capital X, then we know what the power series look like. The question is, can we convert what we have into 1 over 1 minus x form? For this example, it is possible to do that, which the first thing, just like we did before, the numerator, we want it to be 1, but we have x cubed. So we're not going to divide by x cubed. Instead, we're just going to put the x cubed on the side as a factor. So f of x equals x cubed times 1 over x plus 2. And then we're not going to touch the x cubed until later. So now the numerator is 1, that's good. But the denominator is not quite the same, right? Denominator, I have x plus 2, but I want 1 minus x. So I have to begin with a constant first. But I begin with the x in the denominator, so I need to get a constant there. So we're not going to divide by x. We're just going to switch the order between 2 and the x. So that becomes x cubed times 1 over 2 plus x. So now we get a constant to begin with, and then we have an x next to it. But I want 1, so I'm going to factor out a 2 from there, from the denominator. So I get x cubed times 1 over 2 times 1 plus x over 2. So now if we put aside the factor 2 from the denominator, we have 1 to begin with. So we have x cubed over 2 times 1 over 1 plus x over 2. By looking at this part, we're pretty close, right? Except that now we have addition instead of a subtraction, but that's an easy fix, similar to what we did in the previous example. So this plus, I'm going to write as a minus. So I have x cubed over 2 times 1 over 1 minus a negative x over 2. This part is basically the capital X. And I'm only going to focus on this fraction part, the second part, 1 over 1 minus negative x over 2. I'm going to find the power series for that part alone by using the trick. That's x cubed over 2 times sigma n from 0 to infinity, capital X to the nth power. So that's a negative x over 2 raised to the nth power. So now we have an expression with x multiplied with the series. What we could do, just like before, we could bring the term in front of it inside and separate the negative from the rest. So I have sigma n from 0 to infinity, x cubed over 2 times negative 1 to the n, and then x to the n over x over 2 to the n. I'm going to write it as x to the n divided by 2 to the n. We're almost done with this problem to find the power series. The next step is just combine all the terms that we could combine. So that's an n from 0 to infinity. What do we have? We have negative 1 to the n. And then we have a denominator. We have 2, and then we also have 2 to the n. So that's a 2 to the n plus 1. But the x terms, we have x cubed, then we have x to the n. That's a x to the n plus 3. And this is the correct, the final product, final answer that we're looking for. That's the power series representation for x cubed divided by x plus 2. Any questions? All right, I'm not hearing any questions. So the next part is to find the radius of convergence. So again, I'm not going to begin with the very final expression of the power series. Instead, in the middle here, when we use the substitution with capital X, that's what we're going to use. We know that for the boxed part, for this part to be convergent, we have to have capital X in an absolute value less than 1. Translate into lowercase x as a negative x over 2 is less than 1. And then we can solve for lowercase x from here. So that will be getting rid of the negative first, and then multiply by 2. So x over 2 less than 1 in the absolute value, and the x in the absolute value is less than 2. You can write as x minus 0 in the absolute value less than 2. So the 2 here is the radius of convergence. It's a lot easier than trying to figure out what the correct form of x minus a, absolute value less than r from the final part. Any questions on that? Again, I'm not hearing any questions, so please let me know if it doesn't make any sense. Or if I make many mistakes, please let me know. So the next part is the using differentiation and integration to find power series. Because sometimes you might have a function that you cannot convert it to the 1 over 1 minus r form. But if you take the derivative or you integrate, it actually gives you some expression that's easy to find the power series. So suppose we have some function and we know the power series representation for this f of x, which end from 0 to infinity cn x minus a raised to the power of n. Suppose we know that conversion, well, not the conversion, the power series representation for some function f. And suppose that f of x is differentiable on the domain, on the interval a minus r, a plus r, and r is the radius of convergence for this series. Suppose we have this, and then we can say that the derivative of f, so if we take the f of x, we find the derivative, and we want to find the power series representation for that, we don't have to go through all the work to try to find the power series representation like we did with previous example. We could just say the derivative is equal to the derivative of the power series of f. And what is the derivative of that series? Well, that is n from not 0 anymore, it's from 1. I'll show you why that begins with 1 to infinity. And the Cn, so we basically end up taking, when you take the derivative of the series, you take the derivative of individual term. Cn is a coefficient, so it doesn't get affected in the process. X minus a to the n when we take the derivative, so that's a bring exponent in front and subtract 1 from the exponent. So that's the derivative. This expression will give you the power series of the derivative of f. So you don't have to find it from the derivative itself, but you can find it from the power series of the f of x function. Now the question is, why do we have the n from 1, not from 0, like the given function? Well, if we take the given function, expand it, when n equals 0, we get C0. When n equals 1, we get C1 x minus a to the first power, and then n equals 2 term, n equals 3 term. Right? If we take the derivative of this directly, of the expanded form, the C0 is a constant, right? So when we take the derivative, that becomes a 0. And then the next term is probably C1, the next term is some expression. But the first term, when n equals 0, will give me 0. And if I take this expanded form and I try to convert it into sigma notation, I'm not going to include in the 0 because there's no need to, right? So we begin with n equals 1, this term. Well, that's the first term we have in the sigma notation. So that's why we have n starting from 1 for the derivative expression. But for the given function, we begin with n equals 0. So be careful there. So that's the derivative. And then what about the integral of f of x dx? Well, that is equivalent to integrating the power series term by term. Cn x minus a to the n dx. And if we integrate that, it's still a series that doesn't change. N from 0 to infinity. Cn doesn't get involved in the integration. What about x minus a to the n? Well, when we integrate something like that, we just add a 1 to the exponent. But then we have to divide by the new exponent. Right, that's an integration. And don't forget, we have to add a constant c at the end whenever we're finding antiderivative. So those are the shortcuts to find the power series of the integral or the derivative of a given function. And it can be very useful. Any questions here? So here's one example I have. So it says, find the power series for f of x equals 1 over 1 minus x squared. So the denominator is squared, which make it difficult. So which make it difficult to convert to 1 over 1 minus capital X form. It's not easy. It turns out that there's another trick here, which is recognize that, you can call it hint, which is recognize that the 1 over 1 minus x squared, which is basically just the derivative of 1 over 1 minus x, lowercase x. So you can work out the derivative on your own. It turns out to be 1 over 1 minus x squared. Well, how is that going to help? It's helpful because 1 over 1 minus x, that is basically this form, right? We can figure out the power series for that 1 over 1 minus x easily. And then all we have to do is take the derivative. So leave the derivative part. And then what is the power series for 1 over 1 minus x? So that's a sigma n from 0 to infinity, just lowercase x to the n, right? Because capital X and the lowercase x in this particular example is the same. I probably should note that capital X is equivalent to lowercase x. But we are interested in the power series for 1 over 1 minus x squared. So we have to take the derivative of this. So that will become, if we take the derivative, the sigma stays. But then remember that the index when we take the derivative will be different. So n will be from 1 to infinity, not 0. And then take the derivative of x to the n, which is nx to the n minus 1. That's it. So this is the power series representation for 1 over 1 minus x squared. It's not easy if you try to begin with f of x and try to find the power series. But then if you look at it as look f of x as the derivative of another function, then it's a lot easier. Any questions on this? I'm not hearing any questions. So the next example is we have f of x equals natural log 1 plus x. And we want to know what the power series representation is. When you have a natural log of 1 plus x, it's very difficult to convert it to 1 over 1 minus capital X form and then go from there, right? But what we can do is that we can note, if you remember from the past, that if we take the derivative of natural log of 1 plus x, so that will give us 1 over 1 plus x. This is still not exactly the same as 1 over 1 minus capital X, but it's one step closer, right? We at least have a 1 in the numerator. We have 1 to begin with in the denominator. All we have to do is convert the positive to negative. So it's one step closer. So instead of trying to figure out what the natural log of 1 plus x in terms of 1 over 1 minus x, here we just look at the derivative of natural log. Okay, but we're not interested in the derivative of natural log. We're interested in the natural log. So what does natural log? What is the natural log in relation to 1 over 1 plus x? So natural log 1 plus x is equal to the integral of 1 over 1 plus x dx. And with this part, we can convert it into the 1 over 1 minus capital X, and that will give us the power series, which we can integrate to get the power series for natural log. So that will be integral 1 over 1 minus a negative x dx. The capital X is equivalent to the negative x here. So that's integral. Now I'm going to convert this part I'm boxing in green. I'm going to convert that into power series. So that's a sigma n from 0 to infinity, negative x to the n. And then we still have the integral on the side. Before I integrate, so I'm just going to rewrite the negative, separate the negative from the x. So that's a sigma n from 0 to infinity, negative 1 to the n, x to the n dx. And from here, I can integrate the series, which is series n from 0 to infinity, negative 1 to the n, because that's a constant, so it does not get involved in integration. And the x to the n, when I integrate, that becomes x to the n plus 1, and then divide by the new exponent n plus 1. Don't forget we're adding a constant c at the end. So that's how we find the power series for natural log of 1 plus x, by integrating some function that's relatively easier to find the power series for. We're not done with this problem yet because we still have a c, a constant c that we have, but we need to know what c is, right? How do we find the c? To find the constant c, what we're going to do is the left side is a function we know. The right side has a c we don't know. So maybe if we can plug in some x value, then the left side should equal to the right side. That will allow us to find what c is. Now, which value do we use? It turns out that we want the series part to be gone because that series has infinitely many terms. If we have non-zero there, then it's a little bit difficult to find c. So it turns out that we want this series to be gone completely. So we're going to let x equals 0. That's the value we're going to pick. If x equals 0, then the entire series part will be 0. The right-hand side is just going to be 0 plus c, which is equal to c. What about the left-hand side? I have natural log of 1 plus x, so that's the natural log of 1 plus 0, which is just natural log of 1. And if you remember that natural log of 1 is 0, right? So the right-hand side is the representation of the left-hand side, so they should be equal. Therefore, c equals 0. So we found c equals 0, then we can rewrite the expression for natural log of 1 plus x, which is sigma n from 0 to infinity, -1 to the n plus 1, and then x to the n plus 1 power. So that's the power series representation for the natural log function. By integrating some simpler function and the power series of that function. Any questions on that? All right, I have one more example here. I'm not hearing any questions. So the next example, we want to find the power series representation for f of x equals inverse tangent of x. So again, here we have inverse tangent, just like as a natural log. If you try to find the equivalent form for 1/1 minus capital X, it's not easy, right? But let's think about inverse tangent of x. What do we know? We haven't really used it that much, but some of you probably remember that the derivative of inverse tangent of x, which is a 1/1 plus x squared. Not the best expression, but it is pretty good because that's something we can convert to 1 minus capital X. But we are interested in the inverse tan, so that means inverse tangent of x is equal to the integral of 1/1 plus x squared dx. Just like the previous example with natural log. So here we have to integrate a function in order to find the power series for inverse tan. So the process is similar. So I'm going to do a little bit quick. So 1/1 minus negative x squared dx. For this integrand, the capital X is equivalent to negative x squared. And then we can find the power series before we integrate. That's the integral series n from 0 to infinity. Capital X, which is negative x squared to the power of n dx. Again, I'm going to separate the negative from the rest. So that's integral sigma n from 0 to infinity. What do we have? We have -1 to the n, x to the 2n dx. And then the next step is just integrate the series term by term, but we're still going to have a series. And -1 to the n doesn't get involved when we integrate. When we integrate x to the 2n, we have x to the 2n plus 1, but then divide by the new exponent 2n plus 1. Don't forget to add a constant c. We're almost done. Just like before, we need to find c again. So here's the x to a power in the series. So I'm going to plug in x equals 0 in there. So what do we have when we plug in x equals 0? We get the series part is 0, the right-hand side, which has become c. What about the left-hand side? Well, that's inverse tangent of 0. Now you kind of have to think about tangent of an angle give us a value. So inverse tangent means that we plug in value, we get an angle, right? So tangent of what angle give me 0? It turns out to be 0 radians. So happen to be that c equals 0 again in this example. So at the end, we have inverse tan of x equals sigma n equals 0 to infinity, -1 to the n divided by 2n plus 1, and then x to the 2n plus 1. So that's the power series. So this part is equivalent to the Cn. This part is equivalent to x to the n. Any questions on those? So like I said before, that's all I have for today. I don't think we need to squeeze another example in there. Please take a look at the exam. If there's any confusion about grading, please let us know. We will try to fix it. So if you don't have any questions, I'm going to let you go and have a wonderful Thanksgiving. I'll see you next Tuesday. Take care.
Thank you.
Thank you.
Thank you.
Yep. Take care. Thank you.
Wait, could I actually, do you have a second? Could I ask you about an exam question real quick?
Of course. Yep. Let's see. Do you
Yeah,
want
let me,
screen? Do you have it with you?
oh yeah, I have it up. Could I screen sharing permission?
Yep. Yeah. Let me